Good evening, everyone.
Hello.
How's everyone doing?
Great.
Super. I'm Mike Walter. I'm the director here at the Earth and Planets Laboratory, and it's my great pleasure to welcome you here tonight for what I think is going to be a fantastic double header. How many of you were here for our last neighborhood lecture in June? Some of you, yes. I think it was in June, maybe it was May. At the end of that, if you remember, we had a rather lively conversation about sort of the state of play of science in America and sort of the threat to that institution and how it operates, especially with relatively massive cuts to the scientific enterprise. And as part of that discussion, we talked a little bit about some of the programs we have here, and in particular, our postdoctoral fellowship program. And so it made me think, well, this is a good opportunity to hear from some of these exceptional young fellows that we have here at Carnegie, and that's what you get to hear. That's what we're going to do tonight. I wanted to give just a little bit of background. So the typical career path for a scientist, a physical scientist in particular, is to do a PhD. And the projects that you do in a PhD, this is how you're trained in the scientific method, trained to really do research. But those projects are largely the brainchild of your supervisor, and typical in most situations. And then you move on after you've got your PhD. It's a lot of work, sometimes 4, 5, 6, 7 years of your life spent doing this project, or maybe 1 or 2 projects. And you typically move on to a next position, which is called a postdoc or postdoctoral fellow. In some way, this might be grant supported, it might be supported by whatever institution. And these are typically for 2 or 3 years. And sometimes you'll do 1 or 2 or 3 of these. We used to call it the postdoc trail when I was at that stage. It might take you across the country. You might do it internationally. But this is really a very important time in a career, in a scientist's career, because it trains you to start doing independent research. And it's really after you do a postdoc or 1 or 2 that you move into a full-time position in academia, or possibly at a national lab or an international facility somewhere, maybe public policy, maybe in industry, right? But this is the really important training ground for early career scientists. And at Carnegie, we have had a postdoctoral fellowship program for over 80 years, and we're very proud of it. It's kind of one of the jewels on the crown of what we do scientifically, because we basically are able to harness all of this tremendous talent and train these young early career scientists to then move on to these important positions. And they're the future of science in our country and in the world. And again, this is to some degree currently under threat. At Carnegie, we have a program where every year we have a very stiff competition, over 100 applicants, and we are only able to offer a very few of these. It's very important. We're doing all we can to support this program, to try to grow this program. Again, because it is so essential to how the scientific enterprise works in this country. That training to become an independent scientist is absolutely essential. So I'm going to give you the opportunity at the end of this talk to support that if you feel compelled. But before we do that, I want you to hear from a couple of these exceptional young people. One of our staff scientists, Johanna Teskey, Dr. Johanna Teskey, is going to introduce them to you now.
All right, yes, it's my great pleasure. I emailed Mike last week and I was like, can I please introduce them? Like, I'm so excited for this. So thanks for the chance to introduce 2 of our postdoctoral fellows, Dr. Sierra Grant and Dr. Shubham Kanodia, who will give back-to-back talks tonight. I'll start with introducing Sierra, and I should mention that both of them are Vera Rubin postdoctoral fellows, so they have support from money that was from Vera Rubin's family, and she was a staff scientist here for a long time at what was Carnegie DTM, and so we like to think that we're helping carry on her legacy by supporting early career exceptional postdocs. So Sierra got her PhD from Boston University in 2021. Then she pursued a postdoctoral fellowship at the Max Planck Institute for Extraterrestrial Physics, which sounds very cool, where she was a big part of the MINDS program, which maybe you'll hear a little bit about tonight, but it's studies of disks around young stars that are forming planets in the mid-infrared, and that wavelength range is important, which I'm sure she'll talk about. She joined us as a Carnegie Fellow here at EPL in 2024, and has just been doing exceptional work with JWST. She also has lots of ground-based and radio astronomy expertise. And you should keep your eyes out in the press. Sierra and I have been commiserating / chatting about the roots of press releases. So she has one that's coming out soon with some new JWST results. And so keep your eyes peeled for that. Our second speaker, like I said, will be Dr. Shubham Kanodia, who got his PhD from Penn State University in 2022, and then joined us as a Carnegie Fellow. And Shubham has a variety of expertise both in instrumentation as well as pipeline development, sophisticated statistical modeling of different exoplanet data sets. And tonight you'll hear about one of basically his main focus, which is this very interesting population of planets that are sort of surprising, and we might not expect that they would have formed, but he's using them to really constrain different aspects of planet formation overall. Also very impressive in terms of time on telescopes, JWST, ground-based facilities, and he has been a big contributor on our campus to both kind of community events, but also outreach events. If you didn't see, we have flyers for our open house coming up in October. And this Saturday, you could join us at the Rock Creek Park Festival, where Shubham will be there with lots of our other scientists. So without further ado, let Sierra take it away.
Okay, all right. Well, thank you all for being here. It's a beautiful day. I was a little worried that the weather would keep you away if the gas leak on campus or near campus didn't. But it's great to see all of you here and great to be here. Yeah, good. Okay. Okay, so it's a real delight to be here and to talk about my science, the science that I've been doing here as a Carnegie Fellow and that I will continue to do for the next few years that I'm here. So I'm going to be talking about planet formation, how planets form, and what that kind of process looks like. And I'm really going to be talking about this from the lens of using the James Webb Space Telescope. So here's my very, very brief history of the long history of JWST. So this is a picture from when JWST was in development, but JWST really started in the 1990s when the concept for this next generation space telescope really began. Those decades of work culminated in the launch on Christmas Day in 2021. It was a very beautiful and joyous Christmas day for those of us in the astronomy world, because we'd been waiting for so long for this telescope to launch, and to have this wonderful launch was just more than we could ask for. Here's the last image that we have of James Webb as it is launched out into space, where it has been operating for the last 3.5 years, doing incredible science. This is my favorite image from the James Webb Space Telescope. It is one of the early images from JWST. It shows the Carina Nebula here. So in this red-brown color here, this is what we call a molecular cloud. This is a cloud of gas and dust in space, and it is forming young new stars. So you can see one here, and they're dotted all over this image. So this is really a stellar nursery. And so we want to take all of this gas and dust that is out in space, and we have to turn it into the 6,000 exoplanets that we now know exist around stars other than our sun. So somehow we have to take this gas and dust and turn it into those planets. And that's really what I'm focused on. So here's just a schematic of how this works. We start with those clouds of gas and dust. They start to collapse under their own weight, and you have this collapse of this material. At the center, this will form a star that is rotating. Due to conservation of angular momentum, that star will form with a disk of gas and dust around it. That system will evolve. The envelope around this disk will clear, and you'll be left with what we call a protoplanetary disk. In this protoplanetary disk, these dust grains here that I'm illustrating in black, they start to collide and stick together and grow and start to form planets. Eventually, the disk material dissipates, and you're left with something that may look like the solar system. And so Shubham is going to talk next about the planets that we get at the outcome of this process. But I'm really going to be focused on this stage of their evolution, the protoplanetary disk stage, where we think these planets are really starting to form. So here's just the schematic that we have of a protoplanetary disk. We have our young star here at the center. It is accreting material, it's accreting gas from the disk onto the star via the star's magnetic field lines. And then we have our disk of gas and dust. And these go from very near the stellar surface out to hundreds of AU, where an AU is the distance between Earth and the sun. So these are very large structures, relatively compared to our solar system. That's how large our solar system started at the beginning. And there's a huge temperature gradient in these disks. In the outer shielded middle part of the disk, it is very cold. In the hot inner regions, it's very, very warm. You're very close to the star there, and everything is very hot. And so this allows molecules to exist in different phases in different parts of the disk. So in the cold outer part, some of these molecules can exist as ice. And so here I'm illustrating water ice. These dust grains out here are coated in icy mantles. They have icy coatings on them. In the very inner disk, though, it's too hot. It is too hot for the water, in this case, to exist as an ice, and it becomes water vapor in the inner disk. And we think that most planets will form within the inner 10 astronomical units of their host stars. There's many lines to suggest why this is true, but that's where we think the bulk of planets form around their host stars. And this is exactly the region that James Webb is most sensitive to. So when we look at these objects with James Webb, we are really probing the planet-forming regions of these disks. And so how does James Webb do this? Well, James Webb is capable of so much more than just taking the pretty images that we see on the press releases and on the social media from NASA and things like that. And what we're really doing is using James Webb to study the molecules. So here's just this illustration of our water molecule that is bending in space. As that water molecule bends and rotates, it will emit a photon, and that photon will be at a specific wavelength. And if we have many, many water molecules in our disk, they will each produce light at these different wavelengths. And you put all of that together, and you get something that looks like this. This is the molecular fingerprint, a spectrum of what water would look like to JWST's mid-infrared instrument MIRI. And that's the one that I'll primarily be talking about today. So if we see a pattern like this in our data, it means that there's water in that disk that is forming planets. But we can tell not just that water is present in these disks, we can also tell the properties of the water. Because the water spectrum, the molecular fingerprint, will look different if the water is hot versus if the water is cold. And so in this way, we can tell not just what molecules are there and what ingredients are there, but also what their properties are. And it's not just water. Here, I'm just going to show some of the other molecules that are the most abundant that we see. We see carbon monoxide, which is one of the most abundant molecules in space. We see C2H2, acetylene, and HCN, which we think are both important for prebiotic life. We have CO2, which is seen in exoplanet and planetary atmospheres within our own solar system. And so we think that CO2 is a way to link exoplanets with their formation. And we see OH, which is an important molecule in many chemical reactions. It's important in our own atmosphere, and it's also the destruction product of water. And so there's kind of a balance between water and OH in many disks. And so all of this allows us to study the composition and the conditions and the evolution of these planet-forming disks. And so if we take just the model spectra that I've shown here, and we add all of this up, this is somewhat what we would see in the data. But there's one more important piece. We also have small dust grains in the disk atmosphere. And these silicate dust grains bend and stretch, and they produce features in the mid-infrared where we're also looking. And so there's this characteristic bump at 10 microns coming from small dust grains in the disk atmosphere. So this is a model of what the data might look like. And so here is an example of 10 spectra from the MINDS program, just to show you what the real data look like. And so this is brightness or flux as a function of wavelength. And these are all of these different systems. And so what we can see is that there's a huge diversity in the types of spectra that we see in these planet-forming disks. There's differences in line strengths from objects like this one here, where this is not noise, that is all molecules, compared to something that is very line poor. There's differences in the 10 micron silicate feature, indicating differences in the dust properties across all of these different disks. And there's differences in the molecules that we can see in them as well. And so it might not be totally surprising that all of these show this great diversity, because each disk is evolving on its own terms, and it has its own particular properties. It's around a specific type of star. And so this is somewhat the origin of the diversity that we see here in the data. There are disks around small stars, which I'll talk about. There are disks around close stars in close binary systems. And then there are disks around larger stars like our sun. And so the goal is to study individual disks in really great detail in order to learn something about planet formation in those specific systems, and then to use samples to look for trends as a whole. So here's the kind of journey that I want to go on tonight, is I want to look at how the mass or the size of the central star at the center of these disks is playing a huge role in studying the chemistry that we observe in these planet-forming regions. So I'm going to start with sun-like stars. And for sun-like stars, the main focus, our main focus for the past 3 years has been on water. Because water, by and large, is the main molecule that we see in these disks. There's a lot of diversity related to the structure and evolution of these systems, but by and large, water is really abundant in the disks around sun-like stars, which is really good when we're thinking about forming solar systems like our own. And I want to focus in particular on this system here. This is PDS-70. So PDS-70, the star, is slightly less massive than the sun. It's about 75% the mass of the sun, and it's about 5 million years old. So here's an image from the ALMA observatory, so not JWST. But in this image, PDS-70, the star, is here at the center. It is surrounded by a small disk of gas and dust. There is a big cavity here, a big clearing in the material, and then there is a ring of gas and dust in the outer regions. In the cavity are PDS-70b and c. And so you can actually see PDS-70c here. It is surrounded by its own disk of gas and dust that is forming moons. PDS-70b is about 5 Jupiter masses in size, so 5 times the size of Jupiter, and PDS-70c is about 10 Jupiter masses. And so when we look at PDS-70 with JWST, what we're really looking at is this inner disk. And when we did that, we found that water was present. And so if we think about PDS-70 as a young version of our solar system, if PDS-70b and c are kind of Jupiter-Saturn analogs, then this inner disk may be forming Earth-like planets. And if so, we know now that those planets have access to water as they form. Now I want to go to very low mass stars and their substellar siblings. So what do we know about disks around small stars? These are objects that are 20% the mass of the sun and smaller, down to objects that are called brown dwarfs. They're not massive enough to fuse hydrogen, and so they're not, in fact, stars. We know that these objects are shown in abundance, and Shubham will talk much more about these small stars in the next talk. But what do we know about the disks around these objects? And the answer is very little, surprisingly little, because they are very, very faint. And so you need really powerful telescopes in order to analyze them. And so if I show you this image again, this is what the spectrum of a disk around a sun-like star looks like. Here are the first two spectra of disks around low mass stars that we got with JWST. And this was extremely puzzling to us. It was unlike anything that we had expected to see. It was unlike anything we had seen before. And we didn't quite know what we were looking at. Where is the characteristic bump? Here at 10 micron coming from dust. This is seen ubiquitously in other disks. It's absent in these two sources. But instead, you have these big bumps here. We were not sure of what they were when we first got these data. It didn't take too long for us to figure it out, luckily. And the answer is that it's carbon. It's carbon, carbon, and more carbon. So far, we have discovered 7 new hydrocarbon molecules in disks for the first time. So these are molecules made simply of hydrogen and carbon. And we've found them in really high concentrations. And so I just want to walk through this result. This source here that we published in Science in 2024. We see methane. We see C2H4, C2H6, ethane. We see C2H2, which is the most abundant molecule that we see in these disks by far. So much so that we even see its isotopolog, 13CCH2. We see benzene, a benzene ring of these carbons forming this ring here, waving at us. And then we see these long carbon chains, hydrocarbon chains. And we see this really, really regularly. It is not just a one-off system. So here I'm showing the average spectrum. If I take all of our observations and I average them, this is what it looks like for disks around sun-like stars. They have C2H2, this little peak here, and HCN, this peak here, and CO2. But everything else you see there essentially is water. So these are really water-rich disks around these sun-like stars. But you can see, look, the disks around very low mass stars look completely different. And they're full of all of these hydrocarbon chains. And so we figured out fairly quickly what we were seeing in these disks. It's carbon and lots and lots and lots of carbon. But we're still investigating why these disks are so full of carbon. So I don't have a full answer yet. We think that it's related to the evolution of these disks. So it may be that we're seeing deeper into these systems than we are in sun-like stars. So maybe we're just looking down into a different reservoir of material. Or it could be that there's more efficient transport of material from the outer disk to the inner disk, and that's causing the changes in the chemistry that we see. And so I think with other observations from JWST, including programs that I am leading, and ground-based facilities like ALMA, I think that we'll be able to solve this mystery in the next few years. But it was certainly one that took us by surprise and is keeping us very busy. And finally, I want to finish on planets, disks around planets themselves. So what I'm going to be talking about here are what we call planetary mass companions. These are more massive than we're typically thinking about planets. These are about 15 times the mass of Jupiter, so they're pretty hefty. And they exist pretty far from their host stars. So they're still orbiting around their host stars, but we think they didn't necessarily form in the disk around these stars. But these objects are so special because they're actually observable, unlike planets embedded in their host disks that we can't necessarily characterize. And we think that they're the perfect laboratory to study those planets that we can't necessarily see yet. And so this is a system called CT-CHA. We have CT-CHA-A here in the center. This snowflake pattern here that you see is the result of the optics of the James Webb Space Telescope. And so really, the star here is just a point source at the center. CT-Cha-A is a little bit less massive than the sun, but pretty comparable, and it's about 1 to 2 million years old. CT-Cha-B here is this little point of light here that you can see in the image. CT-Cha-B is about 15 times the mass of Jupiter, and it's at about 500 astronomical units from its host star. And if we look at this with JWST, it's really dominated by this bright star. Bright stars are really challenging for exoplanets. You really want to see the faint planet, and it's being buried in the glare of its host star. But if we can subtract off that host star, you can see what the planet pops out here. So this is CT-Cha-B. And if we take the spectrum of CT-Cha-B, this is what you see. And you can see the same exact chemistry that we were seeing in those other low mass objects. We see all of these same hydrocarbon features, including benzene. And this is the first time that we have ever been able to see chemistry in the disk around a planetary mass object. This is a result that just came out last week, and there will be a NASA press release on it on Monday. So this is a bit of a sneak preview, but keep your eyes open on Monday for that. So we're really opening a new door here in what we can do. And so it's really extending trends that we've seen before, now down to the planetary mass regime. So this is a ratio of how bright different features are. This is the brightness of acetylene, C2H2, over the brightness of water. And so things over here have lots of carbon, and things down here have lots of water. And we see a really nice correlation here with the luminosity, or the mass, or the brightness of the host object. And so we can see that this trend continues down now to planet-like objects. In JWST Cycle 4, we were lucky enough to have 2 programs accepted. My collaborator and I, Gabriela Cugno, are leading this program to now extend this parameter space down to include several more planet mass objects with disks. And so we will see if this trend really continues down to the planetary mass regime or not. So here's my kind of recap of what we're learning. The disks around sun-like stars in general have lots of water. There's a great diversity, and it depends on the characteristics of a given disk and its evolution, but water is the main story, which is good for us. Disks around low mass objects instead are full of carbon. We don't know why yet, but it is generally true. About 95% of the low mass objects that we've observed so far have this great excess of carbon. And so we're still investigating why. The disks around planetary mass objects, which we're looking at now for the first time, are also very carbon rich. And so we're hoping with new observations, we'll be able to tease out why this is. But the trends that we're seeing as a function of host mass, we're now doing this around planets as well. And so it's been a really exciting 3 years with JWST. We've learned a lot, and we've raised a lot of new questions. And so I think that the discoveries that we've made so far have just made us all so much more excited for what is still to come. Thank you.
All right, it's a great honor and privilege to be here, to be telling you about some of the research groups that I have done over the last few years, especially because this place is giving me a lot of opportunities to do a lot of the research that I'm going to talk about right now. And it's also wonderful to follow after Sierra, because her research is pretty well connected, and she's done the heavy lifting in terms of introducing some of the concepts. So it makes my life easier now. All right, so I'm interested in big planets, these really massive Jupiter-like planets, around stars that are really, really small. So there are these really faint red stars that are called M-dwarf stars. But before we go there, let's start closer to home with the solar system. So we have the 8 solar system planets over here, and I'm going to be showing this plot quite often, so let me walk you through it. On the horizontal axis, I have the distance of the planets from the star. On the vertical axis, I have the mass of the planets. So Earth is basically on 1 and 1, and then the massive planets are much higher up. As I said, I'm interested in the giant planets, and of those, we have basically 2 in the solar system. Jupiter, the most massive planet in our solar system, and Saturn, It's actually up right now, so you can go see Saturn right after sunset. So we have these two giant planets in our solar system. So now let's zoom into those on the same plot. So now we are seeing where Jupiter is on this axis. And now I'm adding on the right-hand side masses of these objects in Jupiter masses. And as you can imagine, Jupiter has a mass of 1 Jupiter mass. So up until 1995, we just knew of these two giant planets. Shortly after, there was a revolution in the field of exoplanets because it started the field of exoplanets. And we discovered a handful of these giant exoplanets around stars other than the sun. A lot of these were actually discovered by Carnegie's own Paul Butler, who isn't here right now, but he was instrumental in discovering a lot of the planets that I have shown over here. And he did this using this very interesting technique called the Doppler technique. So what we were basically doing is measuring the light from the star and seeing how the star is dancing around because the planet is pulling on it, and the planet is massive, so it makes the star move more. And you can see how the light from the star, when you split it into the rainbow, moves around with time. Fast forward about 30 years, our techniques have evolved a lot, and now we are reliant on the transit method, and these are some of the instruments we use courtesy of NASA, which are basically measuring the light from the star, and as the planet is going in front of the star, it blocks a tiny fraction of it. So we are measuring the shadow of the planet, a really, really tiny shadow of the planet to detect these objects. And what we have now is on the order of 1,000 giant planets that are shown over here. So you can see how the field has evolved in just about 30 years, where we started off with just Jupiter and Saturn. Then we had the objects that Paul helped discover. And now we have these thousands of planets that we've discovered by different techniques. But what I want to do is expand this and actually think about what type of star are these planets going around, because I think that makes a difference. So now if I color these same planets by what type of star they're going around, in blue, we have the solar type stars that Sierra started off her talk with. These are basically stars that are very much like the sun. And in the yellowish colors, I have these M-dwarfs that I'm going to tell you about. And why do we care about these M-dwarf stars? What did they look like? What are these stars? So these stars are much smaller than the sun. They range in mass and radius about 10 to 50% that of the sun. They're not that much bigger than Jupiter. So they're just slightly larger than Jupiter, but much more massive than Jupiter. So there's this intermediate population between planets and more massive solar type stars. But why should we care? Why do we care about these teeny tiny stars, which are so faint and hard to look at? And the reason is because they are everywhere. This is a version of the night sky you would probably see somewhere that's not DC, less light polluted. And that's the version of the night sky you would see if your eyes were just slightly larger and slightly more sensitive in the red. And the reason is because for every star you can see, there's about 10 you cannot, just because they're much fainter and much redder. These stars form about 75% of the galaxy. So if we are trying to understand what is going on in our neighborhood, we cannot ignore what forms the bulk of the neighborhood. So that's what this plot over here is showing. The red stars are the M-dwarfs. That's what we're seeing over here. There's very few solar type stars actually nearby. And those are the ones shown in green. What's interesting is because these stars are so small compared to the sun, planet formation tends to be a bit weird around these. And that's what makes us excited. From a very practical point of view, because the stars are small, it should be easier to detect planets around them. So let's go back to the Doppler technique. And now I have the same animation, but I'm showing an M-dwarf over there. And we can see how the planet that's going around the star is pulling a lot faster onto the star. Another way to think about this is if you had a dog and you were pulling the dog's tail, the dog would move pretty quickly. If you had an elephant and you were pulling the elephant's tail, the elephant would probably not move a lot. And it's basically that. The elephant in this case is the sun. It's much more massive than an M-dwarf. And therefore, even small planets have a huge pull on the host star. And therefore, it should be easier to find these objects. So what I'm interested in, as I started off with, is giant planets. And I call these gems. And given the fact that here at Carnegie, a lot of people study rocks, I need to specify that these are not the gems I'm interested in, but I'm interested in giant exoplanets around M-dwarf stars. So these are these new type of planets that we've been finding that have really kept us up at night wondering what's going on around here. So what we've done to answer this question is started some large surveys. The way we are doing that is first we are using ground-based telescopes like the one Carnegie has in Chile, as well as some other telescopes here in the US, to find these planets and measure their masses. So this is the Searching for Gems survey. We are first mining the data to find these gems. And then once we find them, we look after them with NASA's James Webb Space Telescope. So the problem has been that these objects, which you would think should be easy to find, these are big planets around stars that are small. Why haven't we found them so far? Why is this such a new thing? If these M-dwarfs should have it easier to find planets, why are these objects so rare? And the answer is because up until 2018, we just knew of 2 of these. These objects are so rare that you need to look at on the order of 10,000 stars to find one of them. They're extremely rare giant planets. And that's interesting in its own regard. And I'll come to that why. But what we've managed to do with this survey is grow this sample from about 2 to about 30 now, by virtue of all these facilities that we're using from the ground, as well as NASA's TESS mission. And I think this is extremely interesting and rewarding for me, because not just the fact that we are finding these planets as a virtue of this survey, but also because it's a wonderful training opportunity for a whole number of students across the country and the world, who I think this is an extremely nice way to get started on science. And I think that's extremely important as scientists for us to make sure that we're also training the next generation of scientists in a holistic manner. And that's what this survey has enabled for our program. So I'm extremely happy about that. But let me focus on one planet that I find very interesting, which was called the Forbidden Planet. And I think that was the purpose of the title of this talk. And Katie designed some wonderful graphics. She was somewhere there. So yes, this was TOI 5205. This was called the Forbidden Planet. It got some press attention. But here's why it was interesting. So here we have the sun, and we have a Jupiter-like planet. And this is to scale. So you can see how big the planet is compared to the host star. And now here we have the host star for TOI 5205, which is about 40% the size and radius, the mass of the sun. And you can see how much smaller it is compared to the sun, how big the planet is compared to its host star. And that causes a problem. And this is what makes this planet forbidden. When we think about the amount of material present in the planet, when we think about the mass of the planet and we compare its radius, its temperature, we can get a 0th order estimate of how much mass and metals in the astronomer sense of the word is basically anything that's not hydrogen, helium, are in the planet. So we compare how much metal is in the planet with the amount of metals that Sierra finds in her disks around similar type stars. And basically, the bottom line is the planet is too massive for the disks we think exist around these types of stars. So something is weird. The average M-dwarf disk does not have enough material to form a planet like this. And that's what's causing us pause. So how did this planet form? It clearly exists. We have disk measurements from the work Sierra does, and we have a rough estimate of how much material is in the planet. So something has to give. So let me illustrate that in a slightly different way. Maybe plots will be better. So here I have a plot showing on the horizontal axis the mass of the host stars. On the vertical axis, how much material is present in the disks, like the ones Sierra studies, as well as in the planets, like the ones I study. So here, first in orange, I am showing just disks and how much metals are present in them. Now I add some estimates in these green triangles of the planets that we are finding and how much metal is present in them. So that's the first problem. You can clearly see by eye, it doesn't take a PhD to figure out that the triangles are above the orange lines, so they cannot form in the orange line disks because these have lesser material than here. But the second problem is this assumes that all the material in this giant disks that Sierra was talking about collapses to form a ball that then becomes these planets. And that does not happen. Planet formation is extremely inefficient. So if we have a disk with 100 kilograms of material, just about 10 kgs of those will form the planet. The maximum efficiency we can find is about 10%. So to find a planet over here, you really need disks that are that massive. And that's weird, because such massive disks, as you can see in the sample, we think don't exist. So something is missing in our understanding of disks or in our understanding of planets. But then what we did with Carnegie's Alan Boss is try to use an alternate method of forming planets. So this is a gravitational instability method, which he pioneered back in 1997. So Alan kindly ran some models to predict whether we can form these forbidden planets around these really low mass stars using this alternate method of formation, where you have really massive disks and they suddenly start to collapse because of density perturbations. And if the conditions are right, if the disks are cold enough, you can occasionally form giant planets. So in a nutshell, the answer is if you have really massive disks, so that's what I'm showing on the vertical axis now, the ratio of the disk to the star's mass, you can form these giant planets by this alternate method. But what I want to know is an object like 5205 an outlier? Maybe it's just the peak of the population and we are fooling ourselves. So can we move beyond these individual planets and start to build a sample, a large number of planets, so we can start to do some sophisticated statistics? And that's what we are doing with the GEMS survey from the ground. We are looking at 1 million M-dwarf stars, and the goal is to find 100 of these planets so that provide us enough of a sample that we can do sophisticated statistics without worrying about outliers. And here's an early result, which basically shows on the y-axis the density of these planets, m over r cubed. On the x-axis, you have the mass of the host stars. The colors don't matter. But what I want you to focus on is the fact that as the stars are getting lower and lower in mass, all the planets seem to be approaching a very similar density. And that was very weird. These transiting planets, which is how we detect them, these warm Jupiters, so they're not super hot, have densities that on average seem to not care about the host star they are around. So I started off by telling you, so let's put the pieces of the puzzle together. We have samples of disks where the average disk mass reduces as the host star mass reduces. I told you that these giant planets get rarer and rarer. Around M-dwarf stars, they are extremely rare. Around solar-type stars, they are more massive. And then I told you that when they form, they have similar densities. So we hypothesized that maybe all giant planets are forming in very similar mass disks, which have a minimum threshold. So you need these really massive disks. And once you have them, irrespective of how massive your star is, you can form these giant planets. So this hypothesis brings together the three different observables we have. It connects them together to explain what we are seeing. But this is not all. And the next step here is not just thinking about the densities of these planets, but also their chemistry. So here is a wonderful graphic that you might have seen that was made by Katie. And when we were making this, we were like, how do we make the star look more interesting? So like, okay, it's an M-dwarf star. It probably has star spots on it. And I'll come to that in a second. So we had this for the press release for TY 5205. Then we proposed for some time with NASA's James Webb Space Telescope, and we were lucky to be awarded. And what we are doing now is looking at the planet as it's going around the host star. And then we're using JWST to look at the light coming from the planet, coming from the star, passing through the planet. We basically use a fancy prism to split the light into the rainbow and measure the fingerprints like Sierra does for the disks. We do it for the planets. Because this is such a massive planet, it has a wonderfully deep transit. It's blocking a lot of light from its host star. But those pesky spots turned out to be real. When we look at the data, we see two spots in the data. And when we actually model it, they somehow managed to be exactly where Katie put them. So that was, for the next press release, we should not do that, Katie. So these spots are extremely hard to understand, because when we are trying to measure the composition of the planets through this method, these spots can complicate our measurement techniques. So here is a spectrum of the planet's atmosphere. So like Sierra measures disk atmospheres, we measure the planet's atmospheres. And here is a model that fits it. The biggest component of this is the star itself. These star spots complicate the story so much that about 80% of the spectrum is basically modeled by these spot contaminations. But we do measure the planet's atmosphere. And it's interesting because the only thing we measure in the atmosphere that's really detectable is methane. There's no water on this planet, as far as we can, in the atmosphere of the planet, as far as we can tell. There's no carbon monoxide, there's no carbon dioxide. And again, there are a lot of parallels in the story because, as Sierra was saying, for the solar type disks, though these are the most common species you detect, water, CO, and CO2. So we think what might be going on is that this is not a coincidence. The fact that these planets and these disks are orbiting similar stars, very low mass stars, and the fact that they have similar compositions might be a hint that we should pay attention to. So that's what we're going to try and do with the rest of the survey. We have 7 planets that we have observed with JWST, and we're going to characterize their atmospheres and understand what's going on across the sample of planets and see if we can connect that with the disks and the disk observations we have. So let's look ahead. So we are starting off with these transiting planets that are not really solar system-like. They're pretty close to their host stars, whereas you can see Jupiter and Saturn again. But then what we can do is we look towards the future and add additional techniques to the same picture. So we have planets from the Doppler technique, like the one Paul Butler works on. But then, just about next year, from ESA, that's the European Space Agency's mission, Gaia, we expect to find about 1,000 giant planets around these types of stars in this green region. And this finds planets by a completely different technique, where it's basically looking at the star very carefully, and as the star is wobbling, it's called the astrometry technique. So because as the planet is going around, you can actually see the light from the star, and you measure the position of the star as it's changing with time. And using that, you can detect planets. Shortly after that, with NASA's next flagship mission, the Nancy Grace Roman Space Telescope, we expect to detect thousands, maybe even tens of thousands of planets that are much further away from their host stars. And that's going to be really, really interesting. Because if things go well, with the support of NSF and what Carnegie is also working on, we'll have the Giant Magellan Telescope in Chile. And these gigantic telescopes will actually have the power to directly detect these planets that are so far from their host star, but they'll be able to find them, detect them, and look at their atmospheres directly. And then we can make direct comparisons with, okay, we have Jupiter in the solar system. We know this is what it looks like. We have these thousands, by then millions of exoplanets that we are detecting. What is our place? What is the solar system's place in the galaxy? How did it form? How unique are we? And that's what we like to do. We want to understand how the solar system formed, how unique is humanity in the galaxy, in the universe, and these instruments and tools are just the first step to do that. So let me end over here. So I'll basically end with the fact that while these forbidden planets are going around these most common stars in the galaxy, because of the upcoming missions from NASA and NSF, the future is really bright for these faint stars and the planets that go around them. Thank you.
Thank you, Shubham and Sierra. That was absolutely outstanding. You make it very easy for me to brag about our postdoctoral fellow program. Anybody have questions for either Sierra or Shubham?
This is for Sarah. With all this water out there, how does it exist? In other words, does it exist? Are there a lot like our planet where it's on the surface and it's so massive, or is it more buried in the planet itself? And ultimately, what happens to the water? Does it continue to exist? Does it evaporate? And what percentage generally is it of the planet?
Yeah, that's a great question. So the journey that water takes can be very varied. So we know from the disks, we can see it in ices in some of the disks, and so we can measure kind of the solid content that could be included into planets. And then we see it as water vapor in the disks that I study and the techniques that I study. And so we have a pretty good understanding of the amount of water that is in these disks, but then how exactly it is being incorporated into planets depends a lot on the planet. And it depends a lot on the journey that planets go on between when they're forming in the disks that I'm studying and when we're here now on Earth, so many billions of years later. And so there's a lot of evolution that happens between the time when they're forming and when we're observing these mature planets like Shubham is studying. So it's a really complicated process in trying to link those two. But in terms of the forms that water can take and how much of it is in the core of the planet versus in the atmosphere, it depends a lot on the evolution. And so, for instance, here at Carnegie, there is a lot of work in how water is incorporated into Earth's core and mantle. And so this is, I think, still a very open question in terms of our own Earth, and then extending out to exoplanets is even more complicated. So a lot of work still to do, but it's a very interesting process.
This is a question for Sierra that might turn into a question about the massive planets. When you started your briefing, you said that you were interested in those stellar disks, and the time frame you were interested in was like between 100,000 and 1,000,000 years, roughly. But the sun-sized star and the small red star ought to form at very different rates, or is there some reason they're essentially contemporaries?
Yeah, so we think that they both form relatively quickly. They get to the stage where the disks are in somewhat kind of similar time scales, but their evolution after that is indeed very different. And so sun-like stars, in a lot of the astronomy communities, and stars more massive than the sun, what is the phrase that I'm looking for? Live hard, die fast, whatever the correct terminology that is. But they go quickly. They burn through all of their fuel pretty quickly, and they move on in their stages very rapidly.
So the follow-on question then is, if they're forming relatively quickly, does that enable, if you will, a separation between the M star and its disk? Whereas if it were forming more slowly, maybe the disk would get sucked in to the star?
Yeah, so we think that the disks around these very low mass stars, they're kind of perplexing. We think that the solids, the dust particles really evolve very quickly in the disks around M-dwarf stars and very low mass stars, but the gas disks last a lot longer because they're facing less harsh radiation from their stars, so the gas disks can live longer. So it's kind of a paradox there. I don't know if you want to say anything about planets.
I think you addressed it. Thank you.
Hi, this question is for Shubham. You showed a chart where I think there was like a bimodal distribution of Jupiter-like planets based on the distance of the planet from the star. Is there an explanation for that?
Let me see if I can find that again. Are you talking about like one of the first plots,
Yeah, I think so.
like this one?
Yeah.
That's a good observation. So this is largely because of the fact that our techniques are not perfect. So there are biases involved with them. And the planets that you're seeing encircled from the transit method are easier to find because they're closer to their host star. So they go around the star much more often, and they block the star much more often. That's why we can detect them much more easier. But they are very, very rare. So that's why you need these really big transit surveys to find them. The planets that you're seeing further out at the second part of this distribution are actually much more common, but they don't transit as often. So that's why you need these methods like the transit technique to find them. And these techniques are much more, the non-transiting techniques, the Doppler technique to find them. And these techniques are much more expensive because you basically need to look at a star every few months for decades to find these planets that are so far from their host stars. So that's why you're finding one technique is sensitive to one type of planet, the other technique is sensitive to another type of planet. And that's why what I showed in the end is what we're trying to do, connect all of these different techniques together to not make this look like a bimodal distribution, but a continuum, because that's what we think planet formation should be like.
Yeah, I'm not sure whether this is a question for one or both of you, but when I am thinking about those clouds and the planets and the compositions around the different sized stars, it made me think about running the clock backwards. Before the star formed, and the origin of the original dust clouds, which created that star. And was the process that created those dust clouds, which may have been wildly different compositions, is that from a sloughing off of a nova of a major different type of star? And is this perhaps the origin of these different products?
Yeah, we think that's a really good question. And it's something that we think about too. There's no reason why in like where the stars are positioned in space and in these different star forming regions that we think that they would be different between the low mass stars and the higher mass stars. So we think that there's no reason for the differences there. And one thing that we've done recently in that object that I showed there at the end, CT-CHA-b, which is this planetary mass companion orbiting around this solar type star. We can see in the disk around CT-CHA-b that it's full of carbon. But CT-CHA-a, which I didn't really talk about, which is the host star, it also has a disk. And that disk was also observed in the James Webb observations. And in that disk, we see only water and OH. We see only oxygen-bearing species in the host disk and mostly carbon-bearing species in the disk around the planet. And we think that those formed at exactly the same time from the same exact material. And so that is our best indication so far, I think, that these are forming with the same conditions in the same material, but they're evolving separately. Questions from our colleagues?
Shubham and Sierra, what would you say is the most exciting moment that you've had as a scientist here at Carnegie? Like, is there a moment where you just fell a little bit more in love with what you do? And like, what was it? And could you tell us a little bit about that?
Yeah, so for me, it was easily this planet, the spectrum of the disk around the planet for the first time. A year ago, genuinely a year ago, which is when we started this project, I did not think that that was possible. I did not think that we had the technology or the techniques capable of looking at a moon-forming disk. It was not something that I thought we could do, and it took collaborating with people outside of my direct field. And so we came together. Gabriele Cugno is an expert in high contrast imaging, had the techniques to tease out the data, and then I had the expertise to interpret the chemistry that we were looking at. And so by combining our expertise, we were able to make this discovery that I certainly did not think was possible until very, very recently. And that's something that I'm so excited about for the future.
I'm not sure. I can't think of like a single moment that stood out. But what I do think is very interesting about a place like Carnegie is the wide variety of expertise that's available to answer some of these very fundamental questions. So when I started here, I did not know anything about atmospheres or protoplanetary disks or a lot of this that I've spoken about today. But what's really unique about this place is the number of people who are experts in this, as I said, wide variety of topics, that I go up and to them and talk to them, and then we can start to put together the different pieces of the puzzle. So like I mentioned, Paul Butler, who's an expert in the Doppler technique, Alan Boss in planet formation, Alicia Weinberger when it comes to protoplanetary disks. And I basically go up to them with these weird plots and tell them, okay, now tell me how to explain this. And then we sit for hours at a time and try to figure it out. And then with Johanna, we put together these really cool observing proposals, which gets us the telescope time so we can actually do the science that I've spoken about today and put limits and not just theorize, but put actual observed limits on how these objects are forming. So I think that's the really unique thing about Carnegie.
Anybody else have a question?
Excuse me, when you talk about how much time you get, sorry, on the telescope, what does that translate into in terms of hours per day, seconds per month, or how does that time get allocated? Who makes the decisions about how much time each of you get or somebody else in California gets?
Yeah, so I'll talk about James Webb, and Shubham, I guess he then can say more about the ground-based work. For James Webb, there's a call every year, and so it's coming up in 2 weeks. Yikes. So you have to write a proposal. You have to write a proposal that says, these are the targets that I want to look at. This is the science that I want to do. Here's how I'm going to do the science that I'm proposing and answer the questions that I'm posing. And thousands of applications are submitted to James Webb for all different types of science. So there's planets and disks and galaxies and all of these different topics. And so it's a very competitive process, and they get experts to review all of these proposals. It's a huge time commitment on the community to review all of these wonderful proposals that all should get time, or most should get time. And so it's a time-intensive process. They review all of these proposals. Is the science sound? Are the techniques used going to be able to answer the questions that are posed? Is it feasible? And based on all of that, not very many are chosen. The oversubscription factor is about 10 or so, something like that. So for every 10 proposals, 1 is accepted. And so it's very competitive. Shubham and I have both been very lucky and very successful so far. Hopefully the trend continues in getting James Webb time. So I have been the lead or co-lead of about 100 of hours of James Webb Space Telescope time.
How is that spaced out during the year?
So it depends on the observing cycle and when the objects are up and things like that. But usually for one observing cycle, for one proposing season is about a year. So you can say more about the ground-based work.
Yeah, so for the ground-based telescopes, it works fairly similarly in the sense that most of these telescopes have competitive time allocation processes. The difference is for the space-based telescopes, because these machines are so expensive to build, they're not built by institutions, they're built by governments. So James Webb Space Telescope, the Hubble Space Telescope, and some of these other giant space telescopes have been built by NASA, ESA, and those are the folks you have to request time for through the processes that Sierra mentioned. For ground-based telescopes, you have observatories, like we had a picture of GMT somewhere right there, in places that are extremely dry. You don't want clouds, extremely high up. You don't want a lot of atmosphere above you. So typically places like Arizona, Texas, Chile, Hawaii, and so on. And some of these are run by the government, like NSF. Some of these are run by institutions like Carnegie as well. So one of the advantages of being at Carnegie is that oversubscription that Sierra was talking about for ground-based telescopes is much lower. So it is much easier to get time on these big telescopes to do the crazy science that we come up with and actually see it through to fruition. Whereas that's much harder to do for government telescopes because everyone is trying to apply for time on them, and the oversubscription can be a factor of 3, 5. It's not as crazy as for space-based telescopes, but it can be still difficult to get time, especially like the hundreds of hours that go into some of the observations that we are trying to do. So to give you a sense for the numbers, for the ground-based telescopes, the survey that I am doing has taken about 200 nights of time over about 3 years. But the typical allocation that you have in one semester is in the order of maybe 3 to 5 nights, but we're doing it across a lot of different telescopes. For space-based telescopes, Sierra already covered. For the transit technique, a typical transit is on the order of maybe 3 to 5 hours. So that you want to see in one shot, but then you might want to look at multiple transits of different planets. So that can range from 5 hours to hundreds of hours.
Yeah, I think I just wanted to reiterate the point about, Carnegie and the oversubscription rate being less at an institution that kind of runs these facilities. I mean, Carnegie puts in the investment, and then so that we can reap the rewards of that through this institutional access to these great facilities. I'm gonna add one thing.
I forgot to say at the beginning so the JWST deadline that's coming up is cycle 5. In cycle 2, Shubham was the PI, co-PI of the largest exoplanet allocated program for the entire JWST allocation. So it's very impressive.
And I would add that has very little to do with luck. And I hate to embarrass you, but I understand that Sierra's getting married soon and will be on her honeymoon writing a JWST proposal, apparently.
Well, my fiance is also an astronomer in the audience, came down from Boston this morning to be here. So yeah, that's in 10 days. But JWST is 5 days later, so.
A truly collaborative effort. That
That's
makes
right.
sense.
He understands, he understands.
Are there any more questions? If not, I promised you I was going to give you an opportunity to support our postdoc program. And to do that, you can scan this QR code, or you can go to our website. And when you do that, you can navigate to supporting directly our postdoctoral fellowship program at EPL. There are other options as well. But when you do that, the funds that you had given, every single bit counts. It will go directly to supporting our postdocs, directly to, not right into Sierra's and Shubham's pockets, but they have to travel. They have to go present results at meetings. They have to get to these telescopes. And that's one of the ways that you can support them. And you'll know exactly where your dollars are going to. So if you feel compelled, please visit our website or scan the QR code. That's it for tonight. Our next neighborhood lecture, I believe, is November 6th, where the topic will be the origin of life. So I hope to see you all then. And thank you very much.
Good job. Great job.